Hi everyone, so now we're going to be looking at the actual part of electrolysis. So electrolysis, remember, it's a non-spontaneous reaction and it has delta G to be a positive value. So for electrolysis, you're going to be using the electrochemical series from the data booklet. And remember, these are all reduction potential equations. Therefore, if you need a reaction to be an oxidation, you'll have to flip it over and the sign will change as well. These are the rules for electrolysis. So chaos still applies, where you have at the cathode you'll have reduction and at the anode you'll have oxidation, which means that at the cathode you'll have an equation that's one from these, and at the anode you will have an equation that is flipped. So the cathode is going to be the negative electrode. So in electrolysis, the cathode is going to attract cations. Therefore, it has to be negative. And the anode is going to attract anions. Therefore, it has to be positive electrode. This is reverse for voltaic cells. Now, to determine the reaction at the cathode, we're going to find the most positive reduction potential from the electrochemical series, while at the anode, we're going to determine the most positive oxidation potential. So that's the difference here. Both are looking for the most positive, but at the cathode, we're looking at reduction. At the anode, we're looking at oxidation. So we'll need to reverse the equation and flip the sign from the electrochemical series in the data booklet. Now we'll be talking about aqueous solutions for the HL content. So aqueous means that you have water, that the salt has been dissolved in water, which means that water can be oxidized or water can be reduced. So at the cathode will have reduction of water, and at the anode will have oxidation of water. So let's see the equations for reduction and oxidation of water. So for reduction of water means that water has to be on the reactant side and it has to be gaining electrons. Plus, it's going to be in the same orientation as equations from the electrochemical series. So let's first spot all equations that contain water. Water, H plus, OH minus. So these are the equations that contain water in them. I'm going to, there's one here as well. I'm going to ignore the two equations that are highlighted in red because these contain sulfate and dichromate ions. So we're left with these three equations that involve water. Now, if we look at the first equation, you have water here gaining electrons. So water gaining electrons, this is the reduction of water. And also water is the only reagent here. If we look at this one you see there's H2O, then there's OH, and there's O2. So means that actually, if we look at the reverse equation, it's actually 2OH minus getting converted to oxygen and water. This is actually the oxidation of OH minus. So here OH minus is the reagent. So this is what is going to be oxidized. If we look at the last equation, here you have H2O on this side and then electrons are being produced. So because H2O is alone means that H2O is the reagent. And if we look at the reverse of the equation, this reaction is showing the oxidation of H2O. So from the electrochemical series, we've already seen that we have one equation which shows the reduction of water and one equation which shows the oxidation of water. So these two are very important equations. And we can write down here, reduction of water is this equation where the electrode potential is minus 0.83. And for oxidation, it's this equation where the electrode potential is minus 0.23 volts. So these equations are very important. You should be able to spot them in the electrochemical series whenever you need reactions for reduction or oxidation of water. Now we'll have the cations that will migrate, that will move to the cathode, and the anions that will migrate or will move to the anode. And if it is in aqueous solution, means there's water, so the water is going to go to the anode and the cathode at the same time. But we'll have to decide which one is going to get discharged. In order to see which one gets discharged, we're going to look at the relative electrode potential values. So at each electrode, the more positive electrode potential value is going to get discharged. And the other factor that we look is at concentration. Normally, the one that is in higher concentration gets discharged first, and then the one in lower concentration is going to get discharged second. And also, we have the nature of the electrode. There is inert electrodes and active or reactive electrodes. Reactive electrodes will participate in the electrolysis. We'll see that later on. Let's see our first example of electrolysis. So we have dilute aqueous sodium hydroxide. So first thing that we'll do, we'll identify what are the species that we have. So sodium hydroxide, NaOH, is going to exist in a dissociated form. So species will have Na plus, OH minus, and because it is aqueous means you're going to have H2O as well. I'm going to write H2O twice because part of the H2O is going to go to the cathode, will migrate to the cathode. Part of the H2O is going to migrate to the anode. At the cathode, we'll have reduction, and at the anode, we'll have oxidation. So at the cathode, we'll have Na plus and H2O that will migrate. And at the anode, we'll have OH minus and H2O that will migrate. So let's write the reduction equations first. So we'll use the electrochemical series. We'll find the reduction reaction for Na plus. So that's reduction of Na plus. And we'll find the reduction reaction for H2O, which is this one we've already determined before. Now from these two equations, let's find which one is going to get discharged. So the one that is more positive will get discharged. So the one closest to 0 is this one. So this one is going to get discharged. This is the more positive value. Now let's look at the anode. So at the anode, we're going to have OH minus and we're going to have H2O. Now we're going to have oxidation reaction, which means that you're going to be flipping equations. So because we're talking about oxidation of OH minus, means that OH minus should be on the right hand side of our equation on the electrochemical series. So here I have the oxidation reaction of OH minus, and here I have the oxidation reaction of H2O. So you see OH minus is on the right hand side, H2O is on the right hand side. So now I'm going to rewrite the equations, but I will flip them. And I have reversed the signs of the electrode potential values. Now, when I look at these two equations, I need to find which one will get discharged. So the one that is most positive, the more positive among these two, will get discharged. So it's this one, closer to 0. So this is the more positive value. So I've already decided which equation, which reaction will take place at the anode and which reaction will take place at the cathode. I'm going to combine these two equations now. So these are the two equations that we've decided will take place as they are the more positive electrode potential values. I will adjust the number of electrons so that I can combine these two equations. right? And then the 2 electrons will cancel out. On both equations, I have OH minus, they will cancel out. And I have H2O here and 1 H2O that will cancel out. So I end up with the overall equation H2O giving H2 and half O2. And from this, I find that the ratio of hydrogen to oxygen is 2:1. So for each mole of oxygen, there is 2 moles of hydrogen. So volume ratio is 2:1. This is what is observed when we do the electrolysis. So you have 2 volumes of hydrogen and 1 volume of oxygen, which is shown in the overall equation. The overall electrode potential is just adding these 2 up, and that gives you negative 1.23 volts. And if you look at the overall equation, this is basically the electrolysis of water.